An electrically powered spacecraft propulsion system uses electrical energy to change the velocity of a spacecraft. Most of these kinds of spacecraft propulsion systems work by electrically expelling propellant at high speed, but electrodynamic tethers work by interacting with a planet's magnetic field. Electric thrusters typically use much less propellant than chemical rockets because they have a higher exhaust speed than chemical rockets. Due to limited electric power, the thrust is much weaker compared to chemical rockets. But electric propulsion can provide a small thrust for a long time. Electric propulsion can achieve high speeds over long periods and thus can work better than chemical rockets for some deep space missions. Electric propulsion is now a mature and widely used technology on spacecraft. Russian satellites have used electric propulsion for decades. As of 2013, over 200 spacecraft operated throughout the Solar System use electric propulsion for station keeping, orbit raising, or primary propulsion. In the future, the most advanced electric thrusters may be able to impart a delta V of 100 km per second, which is enough to take a spacecraft to the outer planets of the Solar System, but is insufficient for interstellar travel. Also, an electro-rocket with an external power source has a theoretical possibility for interstellar flight. However, electric propulsion is not a method suitable for launches from the Earth's surface, as the thrust for such systems is too weak. History. The idea of electric propulsion for spacecraft dates back to 1911, introduced in a publication by Konstantin Tsiolkovsky. Earlier, Robert Goddard had noted such a possibility in his personal notebook. In 1929–1931 GG. Leningrad was the first in the world designed and tested electric propulsion. Already in 1950, at the initiative of S.P. Korolev, I.V. Kurchatov and L.A. Artsimovich, it adopted a program of research and development of various electrically powered propulsion with a nuclear reactor was considered by Dr. Tony Martin for Interstellar Project Daedalus in 1973, but the novel approach was rejected because of very low thrust, the heavy equipment needed to convert nuclear energy into electricity, and as a result a small acceleration, which would take a century to achieve the desired speed. The demonstration of electric propulsion was an ion engine carried on board the SERT-1 spacecraft, launched on 20 July 1964, and it operated for 31 minutes. A follow-up mission launched on 3 February 1970, SERT-2, carried two ion thrusters. One operated for more than 5 months and the other for almost 3 months. By the early 2010s, many satellite manufacturers were offering electric propulsion options on their satellites, mostly for on-orbit attitude control, while some commercial communication satellite operators were beginning to use them for geosynchronous orbit insertion in place of traditional chemical rocket engines. Types. Ion and plasma drives. This type of rocket-like reaction engine uses electric energy to obtain thrust from propellant carried with the vehicle. Unlike rocket engines, these kinds of engines do not necessarily have rocket nozzles, and thus many types are not considered true rockets. Electric propulsion thrusters for spacecraft may be grouped in 3 families based on the type of force used to accelerate the ions of the plasma. Electrostatic. If the acceleration is caused mainly by the Coulomb force, the device is considered electrostatic. NASA Solar Technology Application Readiness. Electrostatic ion thruster, colloid ion thruster, contact ion thruster, field emission electric propulsion, microwave ion thruster, plasma separator ion thruster, radioisotopic ion thruster, nanoparticle field extraction thruster, Hall effect thruster SPT, stationary plasma thruster TAL, thruster with anode layer. Electrothermal. The electrothermal category groups the devices where electromagnetic fields are used to generate a plasma to increase the temperature of the bulk propellant. The thermal energy imparted to the propellant gas is then converted into kinetic energy by a nozzle of either solid material or magnetic fields. Low molecular weight gases are preferred propellants for this kind of system. An electrothermal engine uses a nozzle to convert the heat of a gas into the linear motion of its molecules, so it is a true rocket even though the energy producing the heat comes from an external source. Performance of electrothermal systems in terms of specific impulse is somewhat modest, but exceeds that of cold gas thrusters, monopropellant rockets, and even most bipropellant rockets. In the USSR, electrothermal engines were used since 1971. The Soviet Meteor 3, Meteor Priroda, Rosorzo satellite series and the Russian Electro satellite are equipped with them. Electrothermal systems by Aerojet are currently used on Lockheed Martin A2100 satellites using hydrazine as a propellant. Arcjet, microwave arcjet, resistorjet. Electromagnetic if ions are accelerated either by the Lorentz force or by the effect of an electromagnetic fields where the electric field is not in the direction of the acceleration, the device is considered electromagnetic. Electrodeless plasma thruster, MPD thruster, pulsed inductive thruster, pulsed plasma thruster, helicon double-layer thruster, variable specific impulse magnetoplasma rocket. Non-ion drives. Photonic drive does not expel matter for reaction thrust, only photons. See laser propulsion, photonic laser thruster, photon rocket. Electrodynamic tether. Electrodynamic tethers are long conducting wires, such as one deployed from a tether satellite, which can operate on electromagnetic principles as generators, by converting their kinetic energy to electric energy, or as motors, converting electric energy to kinetic energy. Electric potential is generated across a conductive tether by its motion through the Earth's magnetic field. The choice of the metal conductor to be used in an electrodynamic tether is determined by a variety of factors. Primary factors usually include high electrical conductivity and low density. Secondary factors, depending on the application, include cost, strength, and melting point. Unconventional. The principle of action of these theoretical devices is not well explained by the currently understood laws of physics. Quantum vacuum plasma thruster, M-drive, steady versus unsteady. Electric propulsion systems can also be characterized as either steady or unsteady. However, these classifications are not unique to electric propulsion systems and can be applied to all types of propulsion engines. Dynamic properties. Electrically powered rocket engines provide lower thrust compared to chemical rockets by several orders of magnitude because of the limited electrical power possible to provide in a spacecraft. A chemical rocket imparts energy to the combustion products directly, whereas an electrical system requires several steps. However, the high velocity and lower reaction mass expended for the same thrust allows electric rockets to run for a long time. This differs from the typical chemical-powered spacecraft, where the engines run only in short intervals of time, while the spacecraft mostly follows an inertial trajectory. When near a planet, low-thrust propulsion may not offset the gravitational attraction of the planet. An electric rocket engine cannot provide enough thrust to lift the vehicle from a planet's surface, but a low thrust applied for a long interval can allow a spacecraft to maneuver near a planet.